unos puntos, más bien de la parte personal del profesor. Por ejemplo, esta mañana, cuando pasé a recogerlo a su hotel, es demasiado conocido todo el mundo. Pero sí quisiera quizá señalar unos puntos, más bien de la parte personal del profesor. Por ejemplo, esta mañana, cuando pasé a recogerlo a su hotel, había corrido ya 11.8 kilómetros. Si vino a la universidad, regresó al hotel que está en la calle Nueva York, Insurgentes, a eso de las 7 de la mañana y había corrido 11.8 kilómetros. Otro aspecto que los liga mucho a nosotros es su gran participación en nuestro ambiente matemático desde 1956, cuando tuvimos aquí el simposio de topología algebraica. Fue uno de los grandes de ese simposio. Además, en ese momento también recuerdo que quizá Cosul, no sé si Carlos Dimas o Carlos Perelló, se juntaron unos cuantos alpinistas y se fueron al Iztaccíhuatl en 1956. Tenía 49 años y pico. Otros aspectos. Ayer tuve el honor de tenerlo en mi casa, en casa de ustedes, a las 7 de la tarde. Tuvimos una velada muy agradable. Vio que teníamos un piano, se sentó en el piano, tocó unas variaciones Goldberg, tocó un preludio del clave temperado de Bach, con una agilidad de manos, con un fraseo perfecto. Después estuvimos platicando de muchas cosas de música, y es un conocedor increíble de la música buena. ¿Qué otro aspecto podríamos destacar? El aspecto familiar. Cuando lo invité a participar en el Congreso, en la 6ª Conferencia Interamericana de Educación Matemática, que vamos a iniciar el sábado próximo en Guadalajara, me puso una sola condición. Dice, el día de Thanksgiving Day, que para ellos es una cosa totalmente familiar, tengo que estar en Indianápolis con toda mi familia. La única condición que pongo, lo demás no importa. Es decir, que en cualquier aspecto que veamos al profesor Haslow Whitney, es un gran hombre. Entonces, hoy tenemos el honor de que nos platique un poco acerca de una cosa que él sabe porque lo hizo, aspectos geométricos de la cohomología de grupos. Igual.
Muchas gracias. And a few spots you spoke slowly and I understood what you said. And I'm sorry not to continue in Spanish. I have not had enough chance to really study and practice. And perhaps I'll listen in later to find what he really did say about me or otherwise. But I will also try to, for my own purposes, try to speak slowly and carefully. Then you will understand better, and I will also understand what I'm saying better. And I'm not at all used to lecturing for an audience. But more and more I try to make everything a two-way conversation. Let questions come from the outside and from me, so we really get in touch with each other and communicate that way. So at any moment, any of you would like to raise a question or make a comment, and I'll be very happy about that. And with that, I might start right in there and say, first recall what the topic was. Essentially, what happened beginning especially around in the mid-30s. There was this International Mathematical Conference in Topology in Moscow, 1935. Am I right, 50 years ago? Half a century ago. It's quite an event in topology, even in mathematics. For example, Alexander and Kolmogorov both gave the same talk without knowing the other were doing it. By, there's a saying, from two change, I will call them co-change now, X and Y, you can form a product with nice properties, and in the cohomology sense, which is the reverse of homology. in homology, you have, for example, a two-dimensional cell which you orient, and it has a boundary which you orient. So you look at a cell and find its boundary, a very natural geometric thing. The other way around would be to start with an n, with a, call this sigma n minus 1. Look at its, I must erase this now. Look at its co-boundary. All those cells which have it on its boundary have this one and also this one. The co-boundary of this cell is these two oriented similarly. But that is not a good geometric thing, is it? You don't know how. Why should you from there know how far to go? It was natural that cohomology was not used in mathematics up till 1935. But it was used to Congress in that both Alexander and Kolmogorov gave a description of how to get a product in cohomology. Though the factor was too large, they could have divided by a constant to make it right. Then you get rational numbers and not integers. So within a few years, one discovered how to get the right numbers in there. Several people working together on this. I, for one, wrote a complete paper on this subject, which included a product, namely a cochain of dimension r acting on, I'll call it the cap product, acting on a chain of dimension m, which is non-zero if r is less than m. And you get the chain of dimension r less. Let me quickly write down when you do it for change in a good way, the formula for the boundary of the result. Boundary of x cap A is, except for possible sign, I won't write it down now, the co-boundary of x cap A plus or minus x cap the boundary of A. See, all this is dimension m minus r minus 1. This takes away an extra dimension from A. This takes dimension away from a lower dimension. So this shows, the formula shows that it works well if x and if it's a co-cycle and a cycle, then both these terms to drop out, and you get a cycle. And you see that it works for cohomology classes and homology classes to get a homology class. In the geometric sense, to come back to geometry, in three-dimensional space, for example, we might have a surface at A2, and for co-cycle, I'll put it into a complementary form. I'll cut through this. It'll come down and it'll cut. Well, I'll think of it this way: cut through it this way. A sheet like this, cutting all through the middle, and it'll land. The intersection with A will be here's x. X cap A will be that line that's left. But if this is a codimension 1 in your space, this will be a codimension 1 in A2. It'll be a dimension 1 less. So that's a kind of a partial geometric picture of this operation. Now, if you have that operation, of course, then such a product appears easily. You have only to define x cap y by telling its operation on any chain whatsoever. And merely define it as you naturally would, but because you'll want it, of course, to be, start with y cap A, and then apply x to that. So apply first this and then that, and that'll be the definition of the two together. And all the properties. You can do this for the actual co-chains and chains, and of course, for instance, applying it to a cell of the right dimension, you get the immediate definition for over cells of this product. And here, there's not much geometry in this affair. So now, going back to 1935, another simultaneous happening there was Heinz-Hopf presented a paper work of a student, Stiefel, on sets of vector fields on manifolds, in particular three-dimensional manifolds. And that was amazing, because I've just been doing just the same things, sets of vector fields on manifolds myself. I've taken a more general point of view, but got less detailed results on the dimension 3, which Stiefel had gotten. So the basis was the same, but it went in different directions beyond there. However, I had noticed that it was working better in cohomology terms than homology. So I was presenting it in terms of cohomology at that conference. But that is, at least I believe I was. But I also, just before the conference, realized a certain theorem of Hopf on the classifying the mappings of an n-dimensional complex into an n-dimensional sphere, which was rather complex. But the proof was so simple that I felt, why are there complexities in the result, in the formulation, when the proof is so easy? So I'd like to present that now as the first really geometric use of cohomology theory, which really, I feel, that once brought in cohomology and in its natural sense into the subject. So I'll discuss this theorem of Hopf, and I'll use the dimension 2 only. It's clearly the same thing for dimension n. So let's take a two-dimensional sphere and a complex of dimension 2. K, and map it into the sphere. First, of course, we want to simplify the mapping as much. I want to consider homotopy classes. Consider as the equivalent if you can deform one mapping into the other. So it lies over the sphere some way. Let me first take each vertex, if it's mapped up here, and now pull it down some way to the South Pole. I just pull it along this sphere till it gets there. Do that with every one of the vertices. Now they're all mapped into the South Pole. Next, take any one-dimensional cell. It's now mapped into some kind of a curve starting at S and going back there. I can take that curve and just pull it down to S. If it happens to be a curve like this, for example, I could pull it down, or I could spread it out, pull it up over the top and down on the other side, and pull it down a different way thereby. The different ways you can do that. So they'll choose some way to get all the one-dimensional part down to that sphere S. Now we have, for each of these cells, it's a cell sigma 2i. With each sigma 2i is mapped over S with a degree, say di. That's a number of times that this cell covers over the whole sphere. With due regard to orientation, it may be positive or negative, some integer therefore. And as you may know, it's quite fairly elementary. It's a fixed number that you cannot change by deformations. So now we have let's call such a mapping a normal mapping. Put any mapping into a normal mapping so we can discuss just normal mappings. Which ones are homotopic? Well, first, of course, we can arbitrarily choose a mapping, choosing any number di we want for each cell. So we can get any sets of number di we like. We'll get any, that'll be a number corresponding to each cell. I'll call this a cochain. As a chain is to be written as in the form di sigma 2I. But I'll call it a cochain. So we have the d of sigma I. It's a function of cells or of chains. Think of this cochain as linear function over chains. And to look quickly at what this function would be like. Suppose, for instance, we have it something a little like this. Here we would have the sigma, well, the boundary of sigma ni. If we think of that as a cochain acting on sigma n minus 1, in this case it's minus 1 because the orientations that disagree. Or if we look at the co-boundary of sigma n minus 1, acting on sigma n, that there again equals minus 1. So these are the same. And of course, this kind of thing, taking for all the n cells and adding up, right, and so forth, you have that the co-boundary of x dot, let's say r dot a r plus 1 equals x, let's see, well, I'll do this other part, dot the boundary of a r plus 1. That basic relation for any bilinear function is, and this being the dual of the boundary operator. Of course, you have the same thing in differential forms when you integrate them. It's a Stokes theorem in a general case. The change are the real things you would integrate over, and the co-change of the differential forms. I'd like to quickly remark on the terms in differential geometry. You have a countervariant vectors and covariant vectors. The covariant vector is a linear function of vectors. But try the words co and contra. Originally, you have partial derivatives of a function. So this set of numbers corresponding to a function, they said gives you a covariant vector, or covariant vector generally is it's like a French word, a cone. It's with the partial derivatives. And then the contravariant vector is an ordinary vector. Yeah, a vector is a contravariant vector. It's against this kind of a thing. Well, for me, this is the basic element of the vector itself. And so this should be co, and these should be contra. So in thinking what words to use in homology theory, no one had given names, so I chose the names. This other way around, the chain to me will be, what do you call it, a contra chain? We don't need that. But the others are the co-chains. So I chose to turn it around, which to me is better. And it's picked up right away, and that's universal usage now. So different geometries may have some trouble with that. Well, now I think we can very quickly state and prove Hoppe's theorem. We've seen that we can, with another formulation of Hoppe's theorem, we see we can obtain any sets of numbers, any cochain di we like. So how can we change one to the other? Well, first, given one set of numbers, we can take each of these cells and we can pull it up and over the sphere any number of times we want. But of course, the change made is exactly the co-boundary of this cell there, times any multiple we like. And since we can do it for any one we like, we can change it by any co-boundary we like. So that commonly called the X. It's a cochain of dimension 1. We can alter it by any co-boundary we like for an arbitrary Y. Can we do it, alter it any other ways? This we have to check on. So suppose we have X1 and X2. Which are homotopic. Let's see how, see if we can find a Y corresponding. And for those of you who aren't used to this idea, here is how you look at it. A basic tool in topology. Here's my complex. I'll look at a little piece of the complex. And mapped by normal mapping F. I'm going to look at it again, mapped by, that's F1, mapped by F2. And now there's a deformation of one into the other. When I'm halfway through the deformation, I'll have a mapping at least one halfway along. So in general, I'll build up the product of these for the unit segment. Let each cross-section be that mapping is that cross-section deformed. So for example, if you ask about this line, the vertex is moved across. So this, that piece is moved into mapped into some kind of a curve around there. Well, I can take the deformation and change the deformation. I can deform the deformation and get that, pull that all down here. And so pull it down there. Do it for every vertex there. And get a new deformation from one to the other, in which these vertices stay fixed. Now the only change is that the one cells are pulled over. That's exactly what we did already. That proves that these are the only changes you can get. Which proves that the classes of mappings are in a one-to-one correspondence with the cohomology classes of the complex K. Now Hopf's theorem was that they're in one-to-one correspondence with something like the homology classes, but you have to look at torsion. And then it comes in and here's a complex formulation. That merely states that the cohomology classes are in the one-to-one correspondence with some of the arrangement of the homology classes. So this is the exceedingly simple formulation, and his proof is exceedingly simple to give that. So it's a clear use of the cohomology to simplify the statement and proof. The only complication was just in the formulation. So I think one effect this had was to show that that cohomology is an essential part of the topology. Of course, here you see the fact that the co-boundary, which is only to this extent, is our choice of how we'll cut up the complex into pieces. And automatically, it extends that far. Since we pull this round, it'll force the change. We'll restrict how much the change is made. So the geometry is restricted according to how much we choose to restrict the size of these cells. If it were there, then it would go only to there. So the naturalness is less. There's some artificiality still of how we cut up into the cells. But now I want to come to the really interesting, the beautiful, that to my mind, far and away the most important paper of Hopf that he ever wrote. 1942, with the title well, I'll see if I do have it correct. That they took the fundamental group and to see what would happen to do that. Is that the? It's just simply fundamental grouper and zweite Bettische grouper. The fundamental group and the second homology group. They called it the Betty group still. At least he did at that time. And that's, let me give a picture of how, of the simplest case of this, giving an idea that there might be that, more possibilities. We'll take a torus. In the torus, you can go around two different ways. You can start at a point here. You can go around this way, let's say. Or you can start here and go around this way. And neither curve can you shrink to a point. Nor can you make any relation between these two. They're entirely separate. So let's call one of these. Let's call this generator alpha, and let's call this one a beta. And in fact, let's cut it open here. Let's cut this open and pull apart the pieces and follow around. And I'll follow around here and then get back to essentially the same point. So let's call this beta. If you take this and spread it out, we'll get a rectangle. And looking at that rectangle, let's picture alpha here and beta here. Then we go alpha, then beta, then alpha in the opposite direction. See, alpha goes down. This is identified with that, and that's identified with that. And beta in the opposite direction. Following from this point is the same thing as going around like that. And this curve, so let's map this rectangle into the torus. It covers the whole torus. Let's look at just this path and deform it. I can sort them there. Since this whole thing is mapped, I can ask, how is this curve mapped? That's mapped by going around, mostly follows this. It doesn't quite get over here. It's not quite so close to this point anymore. Then look at this mapping there, and so forth. Get that homotopy to a point like that by following right along in the torus. So we have this alpha, beta, alpha minus 1, beta is minus 1, as it's a homotopic to 0, or defines the element 1 in the fundamental group. If we make that mean the class of that. Notice this is a commutator of alpha and then beta. And these commutators are the key to the paper. What happens there? Topologically, when you shrink it to a point, you're forced over a two-dimensional set, of course. In fact, that two-dimensional set is a whole torus. And it's extending this that is the basis of Hopf's paper. Given relations in the fundamental group, that will force there to be two-dimensional parts. Now, what is that relationship? And this, and the geometry of how Hopf started in, I found so intriguing, so beautiful. I've seldom had such beautiful feelings of what you can really do by combining geometry with a careful study. So that I now want to look at. So I will take now a complex K, and we'll look only at the two-dimensional part, but that's what we'll be using. Let's look at the one-dimensional part, K1, and look at the fundamental group of K, fundamental group of K1. Now, for example, here's a path lying in the one-dimensional part, so it lies in G prime, which can be shrunk to a point in K. So in K, this path is it defines the unit element. So that, in other words, it's a relation. So we have relation, a subgroup of G prime. The part which is relations, and therefore defining the identity in G. And G is simply the group G prime modulo the group of relations. Now let's say we've taken a relation there. Let's say the curve lambda is mapped over there and can be shrunk to a point. It has to go over the two-dimensional part. So so that the deformation, describe it by. First, I'm going to take a square to work with a fixed point Q, and in my complex K, I always have a fixed point P. You know, you find the fundamental group in a complex by choosing a fixed point P and have it paths going around it from P back to P. Well, if it deform it to a point, we get the mapping equivalent to the mapping of a, let's say here is a square D with a boundary of D. The curve, right, it's the mapping of the boundary of D. The deformation to a point is equivalent to extending it through the interior. So take this mapping, deform it into a simplicial mapping. If you cut it into small pieces, you can do that. And you have a nice mapping. This will run along in K1, but of course it'll cover lots of cells on the way. So for example, here is a cell it might cover. And there may be some of these covering it positively, some covering it negatively. And taking the algebraic number, we have a chain in the complex. So a deformation made simplicial defines a chain in the complex. I mean, that's a keynote. So we start with lambda and get a chain A of dimension 2. And I would say the lambda is a homotopy boundary, a homotopy boundary for A. And that's the key element for these homotopy boundaries. Now the whole thing a little bit complex. Let's find a simple homotopy boundary. Suppose the chain A were a single simplex sigma n I. Oriented like this, let's say. How can it find a homotopy boundary for that? We have to start at P. Let's choose a path, gamma I, going up to a point there, go around there, then come back. Now we have a path which we can deform to a point, but just pulling right along through this cell. Now we just go up and down, so we pull it all along the path back to P. So that's it, it's a picture in the complex itself, you see. And here is a path which we shrink it down by pulling the path through this here, pull it all down to the P. So the chain we get is exactly, so this path is a homotopy boundary of that elementary chain. And these are easy to see what they're like. So I'll try to use them as much as I can. The first thing we notice is, so I'll write down now, this particular path, lambda I, it's a gamma I, followed by the boundary of sigma I, followed by gamma I to the minus 1. Let's see what would have happened if we'd gone up there by a different path. That's certainly a complication. We might go up here, for example. Let's call this gamma J. And look at lambda J, where you see you go up here, then go round sigma I positively, and back along there. How does it relate to what we had here? Can we do something to that path to get in this path in there some way too? So first we have to go up there. Oh, now we've touched the other path. We'd like to be down there, so why not go down there? So we get down to here. Now instead of going up there, at this point, we can take that and pull it along to down here. And then we'll let it come up again. So that's a simple deformation. And we've now gone from here, first of all, down to here. That's some kind of a path like that, isn't it? Call it a delta. So we can write by a homotopy, we can turn the original lambda j into an equivalent form. I suppose we should put a prime on it, which begins with delta. Then we have to come back here again. Now we can follow along the original lambda j, which goes around here. Oh, but we'd like to go back to b again. Then we have lambda I. So let's again pull a piece down here. We get that back to p. Then we've got lambda I in next. Then we have to snap back to here again. Then we can finish with gamma j. And that last part of it from here on is just delta minus 1, isn't it? So this is an equivalent path, homotopic. By the way, the details are all in this paper, which I will leave for the library here. It's the last section of this paper. And so if you get the idea of it, you can look it up and examine the details with care there. Let's put it into conjunction with lambda I. Lambda j, I'll leave out of this now. Lambda I to the minus 1. We just have to add down lambda I to the minus 1. Oh, and that's a commutator. So let's see just what kind of a commutator it is. The delta can obviously be define any element of R, or any element of the fundamental group at G prime altogether. It could be any path whatsoever in G prime. Or equivalent to it, to any path we like. Given any path in G prime, well, we have, I'll tell you, if we invent a path, let's say, at the mu in G prime, we'll just put the path we have here, then we'll pull it backwards and we'll go over mu. That'll decide us how to find a gamma j. It's obvious we can get anything there. So this, first of all, I don't know what direction I'm doing it from the side. Let's see. Is an element of. I guess that's right. This can be anything. Now the lambdas are in the group R. So let me see if I'm getting this correct. Since we have any element of R there whatsoever, this is a commutator of G prime over the group of relations. So that's we haven't gotten very far, but we've seen that now the elementary ones, by changing this, would make only this kind of a change in it. So this is the kind of changes you can make in general. Now, let's see what the next problem is. Let's see. By the way, we can, of course, get any chain we like. I may not have mentioned that. since we get any cell, we can repeat it, and get it any number of times. Then we can go ahead and do any others too. We get any chain. So we get any chain we like in this way. Now, a basic question is: suppose we've gotten the chain. What are what can we do? Other kinds of things. In particular, suppose that the chain we got was a zero chain. How many boundaries can we give zero? See if that's what I want to look at now. So let's look at that. Then we have to do that anyway for the study here. And I think now I want to look at this D a little more closely. I'll make it larger. So we have an arbitrary homotypic boundary. This is mapped into some kind of a thing, and the interior is mapped. We'll make it all simplicial. And now, first of all, let's cut the D into fine enough parts so we can make it simplicial. We'll cut it up into very small pieces. Namely, these pieces may not look small to you. You just picture it as being many, many times instead of this many times. Let's number these. We have a mapping around here that goes all over the complex, and the shrinking to a point is each of these covers a whole lot of space, all these intermediate things, go back and forth with the complex in some way. Can we reduce them to these more elementary kinds? So let's see. I'm going to begin with the last one, and watch. We went along here. We're going up here, and now we go going around two parts of that cell. At the moment we're going around like that. We went up some kind of a path to that point. Now we're going around. So why not come back again? If we finish going around, so let's add in a piece. Let's add in a piece coming there and coming down here and back here, and of course we have to go back again. And then we get another homotopy. We pull the rest along with it. And we have then, first of all, we've gotten an elementary, perhaps nothing with the original thing here. There's some kind of a place we've gone up here. One of these things going up here somehow. Then we have to come back here, and what happens? Well, then we just go around the boundary of what's left. So we've now found, let's say, original row is equivalent to this row 8, followed by what you'd get row from all the rest of it. So let's now make another change. When I get up here, we'll pull another piece, pull it down around here, and let it come back. So now we have followed by row 7, and what's left is only the first 6. We can keep on like that to row 1. We have it that our the original path is now homotopic to a series of these elementary paths. So we only need to look at them, a succession of them. So now let's examine that succession. Now let's use the fact that that each cell, say this one, it's covered total number 0 of the times. So if it is covered at all, then it'll be positive and negative both, same number. So we can pair the positive and negative off. So there'll be a positive one, let's say with this path going up around it positively, then a negative one, let's say going up this path, then it runs the opposite way. So we have exactly this situation of this that I have raised here, which except where I had the negative, I had lambda j minus lambda I minus 1. That being that's negative path, then the succession we have can be it has that negative in it, just like here. So we have that if they were together, if they happen to be beside each other, we would know it's a commutator. But these may be separated. Something or other here, lambda j, something or other, lambda I minus 1, something or other. And we cannot apply it because there's stuff in between. So what do? We'd like to take this and commute it with that, wouldn't you? Well, let's call this delta. So let's commute it by putting in a commutator. A commutator. We have lambda j. Now, to have it work right, we want to. Well, let's put the commutator in. There's a part of a commutator already. Let's put the rest in. Lambda j minus 1, delta minus 1. Well, we've stuck this in here. We've stuck in the commutator, and now, but we have to get back to this element. So we must remove part of this. This. Well, no, this part is already there. It's this part we've stuck in there. We'll remove that. You have to cancel this out. So delta. Now we have to cancel that out. Lambda j. Now we have our lambda I minus 1 in the rest. So we've stuck that in and we've cancelled it out also. And here is so now we have a commutator there, and now these are beside each other. And notice that's the only difference here. Otherwise, we've gotten that over there, and the delta, we have a commutator in there. This is also in that G prime R. Now this here, we found is in G prime R itself. We have something just like the original, but with these two disappeared, but turned into a commutator. So we use some kind of commutators to get them all rid of them pair by pair. The whole thing is just in the commutator group. And there you have the essence of that. It's exactly that. So now I think I can write down a final formula here for what we have, and then not the final yet. We have to do something with it still. I really want to do one more thing first. Namely, look at another question. In our original lambda, it deformed in some way. Are there other ways of deforming it to a point? We've taken the fixed one and altered it. But are there other ways of deforming it to a point? Let's look at other ways. So let me picture this by mapping a circle. Think of it as it's of a sort of hemisphere of the globe. Mapping this into here, and then the deformation will be mapping a disk bounded by this. I'll put the disk over on this side. So the disk there, we map according to the deformation. But suppose we take another deformation. Look at that one by mapping the other side here. And comparing the two deformations is equivalent to looking at the mapping of a two-dimensional sphere over it. So we can alter a deformation through the mapping of any sphere. That's equivalent to saying the difference between the two deformations. And clearly, any mapping of sphere, we can apply it and make it to do this by just choosing any thing over there, and it gives two deformations. And any deformation we see is equivalent to this. So the so-called spherical cycles mapped the image of any of these things has to be thrown out. So whereas we got to any chain with dimension 2, we really have to consider those chains mod the spherical cycles. And it's those we're really working with. And now we see that we can, of course, get any. We could have got any of these numbers we wanted there. Let's see. I'll get the formula now. Well, I want a representation of any change, but I don't want to use any change. I want to use only cycles. So even with with a two-dimensional chain, I only want to consider the case it's a cycle. What happens then? If it's a cycle, then on any one-dimensional thing, it can have the same number of times going that way as going that way. And the actual path goes back and forth the same number of times. So let's take our path, which defines the zero element here, actually, since of the boundary of A2, and see how we can express that. In other words, what kind of paths the G prime have the property they go back and forth the same number of times over each element. So let's take such a path. So let's say there's a particular time when they go up here. We want to simplify, don't we? Why not simplify by taking every single vertex, choosing a fixed path to the fixed point P. Then every time we've gotten somewhere, we go right back down to P and back again. Then we go to some place, go right down to P and right back again. So now it becomes a repetition of all these things. Let's say lambda 1, lambda 2, which is a succession of paths like these. Very pretty simple paths. And now we can pair these off. There's, when we went up here, let's say the lambda 1, and here we have, when we come back, we first have to go down here, and go back here, and then along there, and go down there before we come back. Exactly the reverse of this one. So here again, will be lambda 1 minus 1, and so forth. So by this simple idea, you get these pairs again, which are inverses. So let's just put them beside each other by commutators. In this case, the commutators are any elements of G prime whatsoever. Then we get these together. Of course, they then cancel out. So we get exactly any element of this group. So those are the paths we're interested in because they define two-dimensional cycles. We'll have exactly the cycles coming by working with these paths. By working with them, we now have that we use only those that are relations, of course. So that's what we were working with. Now we have to take it modulo those which corresponded to zero, the zero chain, which we saw was simply G prime R. And that corresponded to the one-to-one fashion with the two-dimensional group of cycles. I'll call it Z2, that cycle in this cycle, except modulo that S2. And that's the final formula, the basic formula of the Hofstadter paper, which was all coming from the simple geometry of homotopy boundaries. It was then discovered that Schilling had this kind of a formula way back in 1912 or so. And algebraic was an important thing, but here he came in topology. Then Pop's paper went beyond this, getting further things, and all that exploded into an extraordinary mass of present-day theory. I'll just mention this paper of MacLean in 1978, Origins of the Cohomology of Groups. Let's just leave that word geometry. I'll just put in there the word geometry. As to going back to the beginning of the origins and seeing a geometrical part of it. What happened from this is in MacLean's paper. So I recommend that paper to start from this, now with the geometric picture of how it came to be, going on to where it led to in present-day mathematics. So that's, I've been pretty busy and haven't been looking for two-way communication, so I hope we can still have some with any questions or comments of any kind. Why the invariants are...
Why this quotient depends
on the space, not on the complex. On the fundamental group. If we have a different, define a different, for example, a different cutting up the simplexes, define it, the fundamental group is fixed in the complex. But if you define it different ways, well, they give something different. I have to say that I can't answer the question. But that's a good question. I'll leave it to you. It may be answered in there. It certainly is answered somewhere in the material, then or later. The topological invariance of it, and I can't say. That's an important question.
Some other question? Well then, thank you very much, Professor Whitney. We're very glad to have you here.
Thank you.
And we'll hear you again on Thursday at 11 o'clock. Thank you.